Hi guys, Mr. John here. In this video I want to show you this little circuit that I cobbled together from scratch actually, which is kind of fascinating. Basically what this is this circuit does exactly the same thing as the one on my PCB drill press, which is currently torn apart because I'm testing it. But the main difference between this one is this circuit does is it keeps the motor idling at no load. Its motor is idling at low speed, so it's easy for you to aim into with even the tiny fragile carbide bit into the little holes on the printed circuit board you're drilling. This circuit senses the current. As you load the motor up, it draws more current, and when it does that, it goes and turns this LM317 on the heatsink on harder and provides more power for the motor to drill a hole. But the power supply used right there in the base is about 10 volts. And I measured minimum drop across the LM317 of 1.8 volts. So even when the thing tries to effectively have the max power, it won't, because the voltage that the motor will receive will be 1.8 volts lower than the supply, which is 10 volts. So that's kind of sad. So what I did is I went and designed another circuit using a quad op-amp that's an only chip in the whole thing. It's kind of fascinating as well. And what this thing is it uses a MOSFET and it PWMs it to do the same thing. And it works rather good actually. It does have two potentiometers just like the other one, for the same exact reason. This one controls the idle speed. This one controls the point where this thing kicks in and provides max power. They also behave pretty much very similar. If I'm gonna apply power to it, you will see that it will rev up and then calm down. And just like the other one, yes, it whines because the frequency is low. I'll explain why shortly. So as I'm gonna touch it, it will go. I hope you can hear that it revs up. Well, you can see that it revs up. I guess that's enough. So, let me show you what controls do. Alright, very nice. As I mentioned, this controls the idle speed. You can actually hear... you son of a... You can actually hear the motor spinning there, so I don't really need to show you, but... oh well. Right to a stop, but there is still some minimum duty cycle because you can hear the current going there, but we can go and set it pretty much from few percent on to a little few percents from off, from fully on. Let's set the idle. Alright, and this controls the point when it triggers. The more you turn it clockwise, the later it triggers, but this pot might need some limiting resistor to utilize the whole range, because the max range there is about this. About a little bit more than halfway. And if I'm gonna turn it low enough, it will actually behave very similar to a sport bike when the rev limiter kicks in. Not exactly the same, but pretty darn similar. Have a listen. I think that's pretty good actually. This LED doubles as an indicator LED and a reference. And as you can see, when I stall the motor or load it up, it blinks, which means the power supply sags, because it's entering current limit, which is actually perfect, because this supply also, well, it doesn't have current limit, but it kinda drops out if you load it up. So it's mimicking the power supply in the scene very well. Look at the LED. Focus on it and then look. Alright. Alright. Now let's show you the schematic. As again, this thing you won't find on the web until somebody copies me. I don't think they will, but who knows. It uses the LM324 quad op-amp. It has this PWM stuff. This is what creates PWM. This is just a current sense amplifier. That is, iSense is fed right here into pin 3. And there is a comparator, as you can see, which compares the value of current you're sniffing across that resistor to the value you set with this trigger point. And when the sensed current goes higher than your preset value, the output goes high, applies more voltage, pulls up this pin 5, somewhere to the VCC line, and produces a maximum duty cycle. It actually does not have a value in between. It just goes from small duty cycle to fully on. But that's perfectly fine by me. That actually will behave even better than if it had some values in between. So I am perfectly happy. The awesome thing about it is, as I mentioned, it doesn't have that dropout that this thing has. It will be 0 to fully on, because the MOSFET will be switched on fully, so it will effectively be like a short circuit there with a 0.1 ohm resistor. And yeah, I mentioned why the frequency is low. The frequency is low because this op-amp LM324 is pretty darn slow. If you're gonna use a frequency which is like 25 kHz to make sure it is out of audible region, the waveform is gonna look awful. The edges on the square wave will look that square wave will look something like a trapezoid wave. Very nasty. And you don't want those edges to take a lot of time to rise and fall, because during those edges there will be heat dissipation across your switch, and you obviously don't want that, especially here when I designed this circuit purely to maximize efficiency. Not so much because of the power dissipation reasons, but I made it more efficient to utilize all the snot that power supply can put out. Yeah, you can see all the schematic. Here is that LED I'm using for the reference. It produces about 2 volts here, which is where I tap, which is what I use as a reference for this and this point, for idle speed and trigger point. Works really well for what it is. The values here, let me write them. Alright, so this divider resistors 100K, so is this one. This is the timing components 11K and 47 nanofarads, produces about 1.3 kHz, fine by me. And this is little RC filter to make this thing behave, because it's as I mentioned, it's pulsed, quite narrow pulse on idle, so that produces a peak of current, surge of current, which constantly produces a peak here, and thus triggers this, so the thing just goes into that kind of sport bike rev limiter kind of mode. So that's why these components are here. And there is another thing that I forgot to mention. I had actually to AC couple this pin and raise it above the ground about 1.5 volts. Let me show you here. Alright, so here's the contraption. I just used a divider for 70k, 68k to ground, to VCC, which is a power rail, 10 volts in my case, and 82 nanofarad coupling cap. Let me actually show you what happens if I don't have that. I'm gonna show you the waveform. Well, I'm gonna make it a little bit faster. I'm just gonna go and pull out for 70k resistor, and you will see what will happen. Turn it on. Alright, it's misbehaving already. That's kinda sad. Put the trigger point a bit higher. Now. Wow, rev away, my friend, rev away. Why does that happen? Well, it's 11 minutes already. Might as well show you some waveforms. I think you may appreciate it. I created the circuit from scratch, and it amazes the heck out of me that I actually knew what I had to do to fix this kind of Let me show you some waveforms. Okay, I'll be probing pin 9 right now. The load is disconnected right now in order to open the feedback loop. Now, yeah, I'm gonna be probing right here, and we will see. Apply power. The scope right now, that's a 0 line. The scope is DC coupled. See, on the last graticle there. Let me connect it up and show you. So it's pin 9. It's not triggered, but as you can see, the scope is DC coupled, alright? Let me actually set it to 1 volt division, so it's gonna be a bit easier. Pin 9, and as you can see, pin 9, actually that triangle wave you see there has a DC offset of about 3.5 volts. That's 1 volt per division. So what that means, that in order for this thing to work, basically the voltage here and here has to be somewhat similar. Let me draw a couple of waveforms there. Alright, so that's your inverting input. And how it works is the non-inverting input, this guy here, has a DC on it. And it depends where you put that DC. If it's at 0 volts, the inverting input is going to be higher than non-inverting all the time. You'll have 0 on the output. But let's say you put it halfway between the peak, right here. Then you will have pulse, which is this wide. Effectively, it will start right when these two lines intersect, and it will end when these two lines intersect. So higher the voltage on non-inverting input, higher your duty cycle will be, because if you put it right here, it will never switch off. So that's that actually. I showed you the reason. And yeah, actually, one more thing. You might ask, why didn't you then reference this to ground by just putting it like that? Well, it is coupled by a capacitor, see that? It must be coupled with a capacitor, otherwise you will interfere with this oscillator. I'm gonna now scope at the pin 6 with 470k resistor removed. Here's this 470k resistor, you can see away from us. Now I'll go and scope at pin 6, which is inverting input of that op-amp, and the scope is the same, as you can see, DC coupled on the last graticule. Let me touch pin 6, which is this right here. And look at that. Remember, the scope is DC coupled, alright? You can see, let me focus. Remember, the last reticule is ground. See, the waveform dips below ground. That is because of that capacitor action. That's ground. The waveform dips below. What that means that you won't get good enough adjustment on the idle speed anymore. Yep. And actually, I can show you even that. So now I'm scoping right here on pin 7. If this only will make connection. Okay. Here you can see a waveform, right? Now I'm gonna twiddle with this idle speed control. By twiddle I mean just turn it all the way counterclockwise, put this to ground. So effectively you ground this input, alright? And see, we still have a reasonable duty cycle there. Focus, you feck. Alright, now I'm gonna go and put this 470k resistor while you're looking into the into the screen of the scope. Let me aim a little bit. Is it this? Here we go. It's kind of pesky to do, but that's without the resistor, and that's with. See how thin those pulses are now. So this will let you set very low speed if necessary. In my case it's not all that necessary, because even if I remove this and I apply load, what did I change there? Alright, let me make sure it doesn't rev limit. See, it's a minimum speed, and it is actually pretty high. So when I put this resistor in, it will drop to such values that it won't even spin. And now I can adjust it to very low idle speed. To where it just starts moving. See how ridiculously slow that is. Alright, I guess that's it. I'm gonna leave you with schematic, so you can take a look yourself. Alright, let me focus on it. Good. Better yet, I'm actually gonna use all that 53 seconds I have left to show you how the waveform changes as I load it up. You can see it's idle and loaded. It jumps just to 100, but it doesn't really matter. Let me show you how well it actually drills. How do I do that? Alright, let's go and pulverize this board. That's 1.2mm bit, by the way. Alright, that's embarrassing. Tighten the chuck, you dummy. Alright, anyway, you see that it has enough